Here I have a velocity function. I have a graph showing my velocity as a function of time, and I'm trying to understand the motion of the particle. Since I'm starting with velocity, that means I need to be given an initial condition, and I can see here that at t equals 0, I'm given the initial position of the particle. That's going to be important for me. I want to find the particle's position at some point later in time. I want to find out about the velocity, the maximum speed, the turning points, the average acceleration over an interval, and the intervals of increasing and decreasing speed. So the first thing I'm asked is to find the position of the particle at a given point in time. And I know that I have the velocity as a function of time. The relationship that I have there is that velocity is the derivative of position. If I want to reverse that, then I can do an antiderivative of the velocity. But I can really only do a definite integral and find the area under the curve when I have an actual graph. I can't really do a indefinite integral. And what this definite integral is going to give me is the displacement during this time interval from A to B. And so I can use this displacement to find the position in a second step. But to begin, I know the initial velocity, I know the initial position at t equals 0, so I know where I am here. I want to find the position at t equal 8, which is right here, and so I want to do this integral from 0 to 8, from my known starting point, where I have my initial condition, to the place where I want to find the position. And so what a definite integral is when I have a graph like that is the area under the curve. So it's going to start at t equals 0, it's going to end at t equal 8, and basically it is this area. You can think of this as a triangle plus a rectangle. I like to think of it just as a trapezoid, where I have the two bases here are parallel to each other, and this is the height. So this here is the area of a trapezoid, which is 1/2 the sum of the bases times the height. In this particular case, the two bases here are 4 and 12. 4 and 12, and the height is how far apart the parallel lines are. This is 8. And I end up with 64 meters. This is meters per second times seconds gives me meters left. If I'm finding the area like that, it's meters per second times seconds gives me a unit measured in meters, which is what I have here. Now this is the displacement. This is how far I've gone between 0 and 8 seconds. If I want to know my position is defined as the final position at the end of this displacement, and I need to know my initial position. Or I can think of this, by rearranging it, I can think of this as my final position is going to be my starting point plus my displacement that I undergo, as shown as the area under the curve. So in this case, my initial position here is 2 meters. I go an additional 64 meters. And so my final position in this case will be 66 meters. This is a positive quantity, so I'm 66 meters to the right of the origin. The second thing that I'm asked is to find the velocity at t equal 10 seconds. If I have a velocity graph and I want to find the velocity, all I have to do is read that value directly off the graph. A velocity graph tells me what the velocity is. So if I want to find the velocity at t equal 10 seconds, I start at 10 seconds, and I go up to where I find the value on the graph, and then I follow that value over to the velocity axis, and I can say in part B here that my velocity at t equals 10 is going to be 4 meters per second. I'm above the axis, so this is a +4. That means I'm moving to the right, and I'm measured in meters per second. The third thing I'm asked is to find the maximum speed of the particle. The speed of the particle is the magnitude of the velocity, and the amount of the velocity is measured as how far I am above or below the time axis there. So the farthest away I get from this axis is going to represent the highest speeds. And I can see in my graph right here, this is as far as I get from that axis. Every other speed that I'm at is closer to the axis than this point is. So this would be my maximum speed, basically my local max, and I can see at this instant here, at 8 seconds, my velocity is 12. So I can read that off of the graph as well. My maximum speed is 12 meters per second, and that happens at t equals 8 seconds. If I need to know that for some reason, I can go ahead and record all of that. The next thing I'm looking for are the turning points. The turning points are where the particle turns around when it changes direction. As long as the velocity is positive, that means that the particle is moving to the right. If the velocity is negative, the particle is moving to the left. So our turning points we find where the velocity equals 0. That's where we look for these turning points, because that means that the particle is coming to rest momentarily as it stops moving to the right and starts moving to the left, or vice versa. It's moving to the left, stops, and then moves back to the right. Looking for where the velocity equals 0, again, I can look on this graph and I can see where the velocity equals 0 is wherever the curve hits the t-axis, and there's only one location right here. This is at t equals 11 seconds. What I can tell from this is that at 11 seconds, before 11 seconds, earlier on, my velocity is positive. Afterwards, the velocity is negative. So what that means is I had a positive velocity, I'm moving to the right. At t equals 11 seconds, I stop. And after 11 seconds, my velocity is negative, so I'm coming back the opposite direction. So this is definitely a turning point. It's the farthest to the right that the particle goes. The next thing I'm asked is to find the average acceleration. So if I want to find the average acceleration on an interval, I have a definition for that as well. My average acceleration is my change in velocity over change in time. That's what a acceleration measures, is the rate of change of the velocity. In practice, this means delta v means v final minus v initial. That's our standard value of delta. And then delta t is t final minus t initial. Really what this is on a graph is a rise over run. So if I'm looking for the average acceleration on this interval from t equals 2 to t equals 10, well, at t equal 2, this is my velocity here is 6. At t equal 10, this is my velocity there, it's 4. And so the slope here is my average acceleration. And I can see here that my slope is -2. I'm going 2 downwards. That's a negative, means that that's downwards. And I'm going from 2 to 10. That is a distance of 8. And so my average acceleration is -0.25. Acceleration is measured in meters per second. If I wanted to use this equation, I could. I said that my final velocity here was 4. My initial velocity was 6. And my final time was 10 seconds. My initial time was 2 seconds. And this gives me the same answer that I had before. And then finally, I'm asked about the intervals of increasing and decreasing speed. I can see here in this graph, I found my turning point already to be at t equals 11 seconds. I know that my velocity is positive this whole time before then, and my velocity is negative afterwards. I have negative velocity here because I'm below the t-axis. I have positive velocity here because I'm above the t-axis. If I'm looking for intervals of increasing or decreasing speed, that means that I need to know not just the sign, SIGN sign of the velocity, but I also need to know the acceleration. And the acceleration is the derivative of the velocity. And in a graph, this means the slope of the tangent line. When I have straight lines, the slope of the tangent line is just the slope of the line. So what I can do here is I can tell the acceleration is positive in this region because my line is sloped upwards. My acceleration is negative in this region because the line is sloped downwards, and my acceleration equals 0 here because the slope is horizontal. So if I'm looking for speed, for increasing speed when I'm speeding up, that would be in this region right here. My velocity and my acceleration are both positive. My velocity and my acceleration are both positive here, so I'm speeding up in that interval from 0 to 8 seconds. Here from 8 seconds to 11 seconds, my velocity is still positive. I'm still above that axis, so my velocity is still positive here, but my acceleration is negative. I'm angled downwards, so from 8 to 11, I am slowing down. Then as I keep going, here my velocity is negative. Between 11 and 12, my velocity is negative because I'm below the horizontal axis, so my velocity is negative and my acceleration is negative, so I'm actually speeding up between 11 and 12. And then after t equals 12, my acceleration is 0 because I have a horizontal line. If my acceleration is 0, then I'm not speeding up nor slowing down. I'm moving at a constant speed. And so I can use nothing more than my velocity graph to figure out when my particle is speeding up or slowing down.